In this question, the lower end of the spring is connected to a block of mass m 2 kg kept at rest on a horizontal surface. The upper end is being pulled vertically upwards with a constant velocity. Velocity is constant of the upper end, which is u, and this is 0.5 meter per second. Initially, spring is in natural length. Natural length of the spring is 0.6 meter, and spring constant is k, which is 18 Newton per meter. We have to find the vertical displacement of the block in 1.75 seconds and find work done by lifting force, the force which is lifting this end upwards in 1.75 seconds. Find power delivered by lifting force as a function of time. So initially this end is moving vertically upwards, and this spring is in natural length. The spring is not exerting any force. This block is lifted in the case when the upward force is equal to its weight, and when upward force just exceeds its weight, it starts lifting. The critical condition will be the force applied by this spring must be equal to the weight. After that time it will start lifting. Suppose it start lifting at some time t is equal to t naught, and extension produced in this spring will be due to moment of this end only. This end will remain fixed till the block lifts from the ground. So only this end is moving, and extension is created by the moment of this end only. So whatever be the displacement of this end, this will also be the extension in this spring. So we have to calculate the extension produced by the moment of this end, and that extension should be sufficient to balance its weight. So what is the extension required? Let us first calculate what is the extension required. So extension required can be calculated from this k multiplied by extension. I am assuming that extension to be x naught. So k x naught should be equal to the weight, and from here we can easily find this x naught will come out as 0.25 meter. So this much extension is required. At what time this extension is achieved? So only this end is moving, and this end will remain fixed till that time. So this end has to move by this much distance. So velocity is u, and suppose that time is t naught. Suppose at t is equal to t naught, this happens. So u t naught, this is the displacement of the upper end, and it is also the extension x naught. So we know the x naught, we know the value of u from this given value. So t naught can be calculated as a x naught by u, and this will come out as 0.5 second. So at t is equal to 0.5, this block starts lifting. Now we have to find the vertical displacement in 1.75 second. There is no displacement till t is equal to 0.5, t is equal to t naught, there is no displacement. The displacement will be after this time. So let us observe the system at t is equal to t naught. So what is the system at t is equal to t naught? Just I am drawing this system in this diagram. T is equal to t naught. The extension produced in this spring is equal to x naught. Suppose L naught is the original length or natural length, and x naught is the extension. So this is L naught plus x naught at this particular time t is equal to t naught. Velocity of this block is obviously 0 at this particular instant. There is no velocity of this block, so velocity of block is equal to 0, and this end is moving upwards with this much velocity, and this velocity is constant. So it is moving with constant velocity. That means there is no acceleration of this point. So I am observing the system of I am observing the block from this reference frame of this upper point. So at this particular time t is equal to t naught, I am drawing the diagram with respect to an observer which is fixed to this point. So I am observing with respect to the upper point, upper end of this spring, and since there is no acceleration of this point, it is moving with constant velocity. So this will be inertial frame. So I am observing the block from this inertial frame of reference. So what will be seen in this frame? So in this frame, the upper point is like a fixed point. Velocity of block with respect to ground frame is 0. So if I fix this point is now fixed. I am observing block from this frame. So in this frame, velocity of this block will be u downwards. So at this particular instant, t is equal to t naught, which is 0.5 second. Block is moving vertically downwards with velocity u, and there is no force acting on this block. At this instant, no force on the block, no net force, because kx and mg are balancing at this particular instant, and there is no normal direction because it is just about to lift. So there is no net force on the block. We can compare this system by a very famous system, spring block system in the vertical plane, where one end of the spring is fixed with the ceiling and other end is fixed with this block, and this system is released. This kind of system performs simple harmonic motion. So this type of system will perform simple harmonic motion, and the given system, if I observe with respect to this point, so this point will be fixed. So we can compare these two systems, and this type of system will always perform simple harmonic motion. It will perform SHM. So in SHM, at this particular instant, t is equal to t naught. It has no net force, there is no net force acting on this block, and it has velocity u. So at this particular instant, we can say this block is at its mean position of simple harmonic motion. This is the mean position because there is no force at this particular instant. As it goes down, there will be some increase in the extension, and that extension will behave like some kind of restoring force, and that restoring force will be some k times the increase in the extension. So it is going to perform simple harmonic motion, and we can directly write the time period of this kind of motion. So time period of this kind of simple harmonic motion is simply 2 pi under root m by k. So this time period of this simple harmonic motion is 2 pi under root m by k, and if we calculate the value of this time period, so this is 2 pi. What is the value of mass? Mass is 2 kg. This is 2, and what is k? K is 80. It is 1 by 40. 2 pi under root 1 by 40. We can use some kind of approximation here. It is 1 by 4 multiplied by 10, and we can write 10 as pi square. So it will simplify calculations. Pi square, this will come out as pi, this pi will be cancelled, 4 will come out as 2, and 2 and 2 will be cancelled. So it is approximately 1 second. So time period of this simple harmonic motion is going to be 1 second. And what we are given in this situation, we are given the time equal to 1.75. In this 1.75, this we can just subtract this time 0.5. It will lift after, it is going to lift, or it will move after 0.5 second. So we have to find vertical displacement in the interval of 1.75 minus 0.5. So we have to find displacement or vertical displacement, because displacement will be in the vertical direction only. So displacement in 1.75 minus 0.5, just we have to find the displacement in this duration. After 0.5 second, we have to see this duration 1.25 second. What is 1.25? This is 1 plus 1 by 4, and 1 second is equal to 1 time period. So this is t plus t by 4. So we have to find the displacement of this block in this duration of t plus t by 4, that is 5t by 4 second. What is the amplitude of this kind of motion? So it is performing SHM. This is mean position. Suppose this is the extreme position, it will stop here for a moment and again it will go up. So this distance is known as amplitude. So at mean position, we know the velocity, this is equal to u. We have to find the amplitude, and there is a famous relation in SHM, maximum velocity or velocity at the mean position, which is a maximum velocity or maximum speed. This maximum speed is equal to amplitude times angular frequency, and from relation k is equal to m omega square from SHM, omega can be written as under root k by m. So this omega is under root k by m. So this is a under root k by m. From here we can find amplitude equal to u under root m by k. And if we put the values just like we have put for time period, so this will come out as 1 upon 4 pi. If we calculate in terms of pi, I have put pi square is equal to 10, or if you simplify further, so this will be equal to approximately 0.08 meter. This is the amplitude of this kind of motion. So where will be this block, the position of this block at this particular after this particular duration, which is t plus t by 4. This is one time period plus t by 4. So initially means when it is about to lifting, initially it is at the mean position. In one time period it will complete its one oscillation, and after one time period it will be again at this mean position only and going downwards. In t by 4 it will move from mean position to extreme position. So effectively in this interval of 5t by 4, its displacement is in the downward direction with respect to the upper point. And what is the displacement? What is the magnitude of displacement? So this is equal to a, because in one time period it is at the same position, so displacement is 0. Whatever I am talking, displacement or anything, I am talking with respect to this frame. I have fixed this point, I am looking the block from this frame only, so whatever I am talking is with respect to this frame only. So it will be here at after a duration of 1.25 seconds, it will be here. So this displacement is effectively equal to this amplitude. So this is the displacement of block with respect to the upper point, but we have to find the displacement with respect to the ground frame. So let us first find the displacement of block with respect to this upper point. So displacement of block with respect to the upper point, let us assume this upper point as P, upper point P, this is equal to A downwards. And what is this A downward? This is 0.08 meter downwards. This is the displacement. What is the displacement with respect to ground or with respect to left frame? Displacement of block, this is with respect to ground, so this will be equal to displacement of block with respect to point P. Now we have to add the displacement of P also from vector displacement of point P. We have to add this to vectorially. So what is displacement of block with respect to P? This is 0.08 downwards. So I am using -4 downwards, 0.08 meter, and displacement of point P with respect to ground will be obviously in the upward direction. And this displacement, let us calculate this displacement here. This is u into this time interval, and what is u here? This is 0.5. What is this time interval, which is 1.25 second? In time interval of 1.25 second, this is the displacement of point P. So just add this 0.5 into 1.25. If I add these two displacements, then I will get the answer as 0.545 meter. So this is the answer for the first part. This is the vertical displacement of block with respect to ground. Now let us come to the next part, which is work done by the lifting force. And for finding the work done by the lifting force, I can use work energy theorem. From work energy theorem I can write work done by the lifting force, and there is no non-conservative force, so I am writing potential energy for all the conservative forces involved in this question. So work done by lifting force, this would be equal to the change in kinetic energy plus change in potential energy. And potential energy is of two types in this particular situation. One is gravitational potential energy and other is spring potential energy. For writing change in kinetic energy, I must know the velocity of block initially and finally. For writing delta U gravitational, change in gravitational potential energy, I need to know the height raised by the block, and for writing change in potential energy, just I need the extension in the spring initially and finally. So what is the change in kinetic energy? Initially block was at rest obviously, and at t is equal to 1.75, at t is equal to 1.75, the block is here. This is the location at t is equal to t naught, and this particular location will be at t is equal to 1.75. This is t is equal to 0.5 second, and this is at t is equal to 1.75. It is at the extreme position, its velocity is 0. Its velocity is 0 with respect to this point P. It is not 0 with respect to the ground. If you want to write the velocity of this block with respect to the ground, then we have to add the velocity of P in this velocity. All these velocities in this diagram are with respect to P. So velocity of this block with respect to ground will be equal to velocity of a block with respect to P plus velocity of P. And at this particular instant, this part is 0, velocity of block with respect to P is 0. So only we have to write velocity of P, and velocity of P is always constant. This is equal to U. So change in kinetic energy is simply half mu square finally, and initially kinetic energy was 0. Delta U gravitational, we know the height raised by the block, so we can write delta U gravitational. What is the change in spring potential energy? Initially spring was in natural length, so there was no spring potential energy initially. For final spring potential energy, I need to know the final means what is the extension at t is equal to 1.75. so at t is equal to t naught, till t is equal to t naught, or at t is equal to t naught, the extension in this spring is 0.25. so extension at t is equal to t naught, it is x naught, which is 0.25. Okay, this is already calculated. It was 0.25 meter at t is equal to t naught. And after that, what is the further extension? We can easily write the further extension from this diagram. I am keeping this point is fixed. Whatever this block will move will be the further extension of the spring. So further extension, this block is now here at t is equal to 1.75. so further extension will be equal to a. So we just have to add this value a in this initial extension, and we will get the final extension. Initial extension means at t is equal to t naught, what was the extension before lifting. So at this particular instant, the extension at t is equal to 1.75. extension, let us say it is equal to x, and x is equal to the initial extension plus the further extension 0.08, which is 0.33. This is the extension at this particular instant. So let us write the expression of work. So work done by this lifting force is equal to change in kinetic energy, which is half m and u square. And what is in the value of u here? U is 0.5. Change in gravitational potential energy, this is mg multiplied by the height raised. Potential energy change is positive. Half k is 80, and this is 0.33 square. Initially spring was in natural length. If we add all this, we will get 15.5 joule. So this is the answer for work done by the lifting force. Now the next part, which is power delivered by the lifting force. And for that, for power, we know power is equal to Fv. F and V are in the same direction. So power is equal to this F into V. We have to find this lifting force, and this lifting force at any instant will be equal to the spring force. At that particular point, that lifting force must be equal to the force applied by the spring. And what is force applied by the spring? Which is k times extension. If we just find the extension, then we can find the force applied by the spring. So velocity, as far as velocity is concerned, velocity is always u, so this part is constant, we need not worry about this. For force, this is equal to some k into extension, and k is obviously constant, so we just need to find the extension, and we have to find the extension in two steps. The one step will be before lifting the block. So before lifting, this extension will be produced by the moment of the upper point only. So extension, I can write it as velocity of the upper end multiplied by the time duration, which is equal to t. So for extension, I can write ut. Before lifting, let's write it as t less than or equal to t naught. T naught is 0.5 here. So this power is equal to lifting force. Lifting force is spring force. Spring force is some k into x. X is ut. So this is the force and this is velocity. So this is ku squared t. This is the lifting force for t less than or equal to t naught. What is after t greater than t naught? Suppose I denote t is equal to t naught. I denote this instant as t dash is equal to 0. Suppose I start a new time coordinate here, which is denoted by t dash. Let us assume that t dash is equal to 0 for simplicity. If this t dash is equal to 0, then for this t dash is equal to 0, so I am referring this instant, this particular instant at t dash is equal to 0. So my this instant is t dash is equal to 0 instant. At this particular instant, the block is at the mean position, it is going towards its extreme position. I have to write the equation. I have to write the equation of moment of this block, equation of SHM of this block. The SHM equation of a block which is at the mean position is of the form x is equal to some a sin omega t, where x is the displacement from mean position. So displacement I can write some a sin omega t. We have to decide, we have to write minus a sin omega t or plus a sin omega t. We have to anyhow find the extension. So extension at this particular instant, extension is equal to this 0.25, and that extension is equal to ku square t naught. If we put the value of t naught, we can find the extension at t is equal to t naught, exit time t is equal to t naught. And from this diagram, in this particular diagram, extension is 0.25 meter, and after this instant, this block starts coming down in this particular frame. So this point is fixed, this is moving in the downward direction, that will increase the extension in the spring, and whatever be the displacement of this block will be the extension, will be the further extension in the spring. So I have to add this displacement of the block plus 0.25. So 0.25 plus this displacement of block will be the extension in the spring, and that displacement is of the type of some a sin omega t. So let me write that. So I am writing the extension for t greater than t naught, and I am denoting t is equal to t naught at t dash is equal to 0. This is the new time coordinate. So 0.25, for 0.25 you can also write ku square t naught. So 0.25 plus, sorry, and this is the power, extension is ut naught. This 0.25 is ut naught. This is a sin omega t dash. Now you can see, as the time is just greater than 0, t dash is just greater than 0, this term will be positive, and initially the extension is also increasing. So we have to use the sign of plus, we have to use plus sign here. So we are perfect, plus a sin omega t dash. For 0.25 you can replace it from ut naught. For a you can replace it by, if you need, you can replace it by 0.08 meter, or you can replace it by u under root m by k. I'm replacing it u under root m by k. So this is u under root m by k. Sin omega, omega you can write k by m. For t dash you can convert it in terms of t also. So what is this t? For t greater than t naught, we can write t as t naught plus t dash. We can easily write this. So t dash is equal to t minus t naught. You can replace t dash by this. So I can write t minus t naught. So this is going to be the extension at this particular instant. So this is the extension. Extension multiplied by k. This is the spring force. Spring force multiplied by velocity u. This is going to be the power. So this is power for t greater than or equal to t naught. You can simplify it and write. You can write it like this. U is common from this, and u is also here. It will be ku square. So this is ku square t naught plus under root m by k sin k by m t minus t naught. So this is power for t greater than t naught, and this is the power for t less than or equal to t naught.